Alright, this is Lab 2, Motion of a Falling Object, done by Sujit Munigani. So, for an introduction for this lab, the objective is to observe an object's motion as it falls towards the ground. This experiment will compare position as a function of time, with two cases of experimental measured position, one using tracker, and then the second case being two computational models using Python and the momentum principle. A brief summary as to what actually happened. The object gained velocity as it falls toward the ground as a result of a non-zero net force being applied to it. So a big component of this experiment is using the momentum principle with two main formulas, the velocity and position update formula. The velocity update formula, which is just updating the velocity, final velocity is equal to the initial velocity plus the net force divided by the mass times delta time. In this case, we have a non-zero net force, which would mean that the velocity would be changing. We drop an object from rest, so there is no initial velocity. The position update formula is just the final position is equal to the initial position plus velocity times time. Both these formulas will be used incrementally through our computational models. So here's the actual tracker video clip that I analyzed. And so, as you can see, the ball, or the crumpled up sheet of paper, just drops toward the ground, and the data points were plotted as such. And so, the general components of this experiment, the mass of the crumpled up sheet of paper had a mass of 0.0045 kilograms. Both the velocity position started at 0, velocity was at rest, so both are 0 vectors. And then there was a gravitational constant of 9.8 meters per second squared. For the weight-only model, there's only one force, which was just the weight, gravitational weight, which is just negative g times the mass of the ball times the unit vector of j, and then net force is just that, and then we, based on that, it goes into the velocity update and position update formulas as such, and then it updates as time is less than 0.667. For the drag force model, it's about the same thing except one more added component, which is just the drag force modeled by negative b times v squared with the b constant of some unknown number. In order to find the b constant for this, I had to guess and check a bunch of b values until it matched my tracker data, and I came upon a value of 0.0004. And so now the net force is just comprised of the weight force and then the drag force, and then the same velocity and position update formulas. And so with those three models, I was able to compile a graph with the blue being the tracker, red being the weight force, and yellow being drag. As you can see, both blue and yellow end up at the same point, meaning the drag force is really helpful. There is some gap, but that could be due to acceleration, which can't really be addressed, but they do have a final position that's equal, and then the weight force travels a farther distance in the same amount of time because it doesn't have the drag force countering upon it. And so some possible error that could have occurred when the object was dropped, it didn't fall completely straight down. It's not too big of a concern, but it's still important to make note of. In the gravity-only model, the velocity starts from 0 and continues to change at a linear rate, showing no signs of reaching terminal velocity. However, in the drag force model, the velocity starts at 0, but it begins to show signs of sloping off, indicating that it's reaching terminal velocity in the future. Terminal velocity occurs when drag force cancels out gravitational force, meaning that there's a net force of 0, and because of that, it would mean a constant velocity. If an object was initially thrown downwards, the terminal velocity would be the exact same as if it was dropped from rest. I did this by going into my computational model and adding an initial velocity of negative 5 meters per second, and this graph came up. Whether there is an initial velocity or not, the terminal velocity won't change, and just to prove it again, I started with an initial velocity of 0, and it came to the same exact terminal velocity of about negative 10.5 meters per second squared. Thank you.